This module is going to be much shorter and hopefully a bit simpler than Module 11, which you just finished, in part because I am not going to require of you to do any computations, any calculations whatsoever. I am going to talk about factorial ANOVAs in a strictly theoretical and conceptual sense, so that you can understand what they are and how they work, but you won't have to actually compute one. In real life, statisticians really don't compute these. They have a computer do them, and so I want to have you understand what the computer might be doing if someday you take a more advanced statistics class and you have the computer compute one for you, so you can interpret it and understand what's going on. Remember from our last module that we learned what were called one-way ANOVA designs. These can also sometimes be called simple ANOVAs or single-factor ANOVAs. But what defines this type of ANOVA is that they only have one independent variable. An example of this might be something like, does the method of communication that you use impact how emotionally close you feel to the other person that you're communicating with? You might communicate with them in an experiment using one of four conditions, either in person or over Skype or over the phone or over text. And you can rate your emotional closeness to that person on a 10-point scale. And so in each of those conditions, we might compute a mean across multiple people, and we would say the people who talked in person felt very close, Skype less close but still reasonably close, phone less close but text more close than talking over the phone. I just made these up, so I don't know what kind of results we would really find, but the reason why this is called a one-way ANOVA is because this is one independent variable. It has four levels, or four conditions, but all of the conditions fall within one type. It's communication type. So the independent variable, or the factor, in this situation is communication type. You would compare in a one-way ANOVA, just like we did in our last module, if there are any differences between the means of these conditions. And if there were, then we would call this a main effect. A main effect. A main effect means that there are mean differences somewhere between the levels of an independent variable, or between the levels of a factor. You can do two types of one-way ANOVA. You can do a between subjects or a within subjects. A between subjects is where you have separate people in each of the conditions. So the people who were communicating in person would be different than the people who were communicating via Skype, and the people communicating via phone, and different people communicating via text. And maybe in each of these groups you might have like 30 people. So 30 people came into your laboratory and they communicated in person. 30 other people came in and they communicated with somebody over Skype. And 30 more people came in and they talked over the phone. And 30 more people came in and they talked over text. That's a between subjects design, because you are comparing the differences in the means here between the subjects. They're separate subjects, so you're comparing between them. But we also have this within subjects, which is, we learned this term and a similar term, repeated measures, back when we were talking about t-tests that were repeated measures t-tests. We learned that the phrase within subjects refers to if you use the same people and you're comparing within those people. So within subjects would be if you took 30 people and you had them come in and communicate via in-person communication, and then via Skype, and then via phone, and then via text, and you might counterbalance them so they do them in different orders so that they're not always in that same order. But the point is that you've taken 30 people and you've made them do all of the conditions. So you can do a one-way ANOVA with different people or with the same people across your conditions. A factorial ANOVA is what we're going to be talking about in this module. Now we already briefly touched on the idea of a factorial ANOVA in our last module, but I just want to kind of explain what the purpose of a factorial ANOVA is. In real life, independent variables rarely have an isolated effect on dependent variables. So you'll remember that independent variables are those variables that you think have some kind of causal relationship or some kind of impact on, or you're interested in the relationship between these things that you might have control over or that might vary across people, and these independent variables will impact dependent variables that you aren't controlling but that do vary across individuals as well. But one independent variable isn't going to impact dependent variables in isolation. It will usually work in concert with other independent variables. So, for instance, do you think that therapy will always work? Or do you think there are things that will make therapy more likely to be effective in some circumstances compared to others? If therapy works when the therapeutic alliance, for instance, is strong, but doesn't work at other times, then it would be inaccurate to lump all therapy together and evaluate it without considering the alliance. So, the therapeutic alliance is this idea that when a therapist and a client meet together, if they both feel that they're on the same page, working towards the same goals, in agreement about antecedent conditions, if they feel like they click, kind of get along, enjoy each other's company, then there's this relationship between them that we term the therapeutic alliance, that agreement or the alliance between them. If you have that with your therapist, there's lots of research that kind of shows it doesn't matter what therapeutic techniques your therapist uses. It's kind of like any therapy will be effective as long as you have that alliance. And if you don't have that therapeutic alliance, it doesn't really matter what strategy your therapist attempts to use with you. It's kind of not going to work. And so we could say that therapy will be effective if and only if the therapeutic alliance is strong. A factorial design allows us to consider more than one factor. Remember, I taught you in the last module that the word factor with an IAL at the end means more than one factor. So if in a situation where we're investigating people's mental health before and after treatment, we might collect 100 participants and we might measure them before treatment and after treatment, and their mental health might have improved to some degree. But this is only one independent variable before and after treatment. One factor. If we use a factorial design, we could look at both before and after treatment, as well as the therapeutic alliance in the same research scenario. And that might look more like this. You could still have before and after treatment, but you could also have separate lines to represent those people who don't have a strong therapeutic alliance and those people who do have a strong therapeutic alliance. And you would see then that the therapy doesn't work at all for those people who don't have one, and it works remarkably well for those that do. And on average, it looks like it works a little bit for everyone. But if you consider the therapeutic alliance in a factorial design, both at the same time, then you realize that it's not working a little bit for everyone. It's working a lot for some people, and not at all for other people. So, no doubt you remember from the last module that I showed you this table here, where we had a therapeutic technique with a couple different kinds of therapy, and then we had a time factor that was before, after, and a 6-month follow-up. I told you before that there are 2 factors here, therapy technique and time, and that there are levels of each factor. 1, 2 levels of therapy technique, and 1, 2, 3 levels of the time factor. We would call this a 2x3 ANOVA if we were comparing the means for this group versus 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 this group. If we compared all 6 of those means, we would call this a 2x3 ANOVA. 2 levels of this one, 3 levels of this one. So you could notice from calling it a 2 by 3 that there are 2 factors, because the first one right here is a factor and the second one right here is a factor. So you add up this first one and the second one to say, oh, there's 2 factors because there's 2 numbers in this blank by blank. And the first number indicates the number of levels in the first factor. Remember, the first factor is therapy technique, so we have 1, 2 levels. And this number represents the number of levels in the second factor, 1, 2, 3. So you can see 3 levels in the second factor. But ANOVA is flexible enough that we could actually shake things up in a lot of different ways. For example, I indicated before that we could do between subjects and within subjects one-way ANOVAs. Well, in a 2-factor ANOVA or a factorial ANOVA, we could run both variables as between subjects or both variables within subjects. Or we could do what's called a mixed design, where one of the factors is within subjects, repeated, and the other one is between subjects, different people, different groups. So here you'd see that we're comparing those that have a strong or a weak therapeutic alliance and comparing them before and after treatment. In this situation, if you look at the means of these conditions, you can see that just like I demonstrated on the last slide, there isn't, it seems like there's no effect of the therapy for those with a weak therapeutic alliance. So before they had a score of 10 and after they still had a score of 10. But if you have a strong therapeutic alliance, then you might start at 10 and after therapy you might have a score of 20, so your mental health will have improved. We would call this a 2 by 2. We could also do what's called a 3-factor design, where you include 3 different independent variables, or 3 factors. We would call this one a 2 by 2 by 2. And you could see that there are 3 factors. Here's the first, here's the second, here's the third, and each of those factors has 2 levels in it. So we've got the same therapeutic alliance, weak and strong, as before, the same treatment before and after as before, but here we've added a 3rd dimension, and that's gender, male and female. We could even do a 4-factor design. Statistically, you could do more, but it's beyond our mortal minds to understand that, so probably best not to. But you could, for instance, have the same block of variables that you had before, which would be weak versus strong therapeutic alliance, before and after, male and female. But then you could also add this dimension of wealthy versus poor, and you would have all 3 of those variables for wealthy folks and all 3 of those variables for poor folks, which would make a 4th variable here of wealthy versus poor. And we would call this a 2 by 2 by 2 by 2, because we've got the first independent variable has 2 levels, the second independent variable has 2 levels, the third independent variable has 2 levels, and the 4th independent variable has 2 levels. So it's 2 by 2 by 2 by 2, 4 factors, 4 independent variables, each with 2 levels in it. I'd like to take a moment and drill down into the simplest case of a factorial ANOVA. The simplest case is a 2 by 2. Why? Because in order to have a factorial ANOVA, you have to have at least 2 factors. One factor would be a single factor or a one-way ANOVA. So in order to be called a factorial, you have to have at least 2 factors. And in order to have the simplest case, each of those factors have to have the lowest number of levels that you can have in order to be considered an actual factor. And that's 2. Because if you only have 1 level, that's not actually a factor at all. You're not measuring differences across something if everybody is the same. So each of the 2 levels has to have at least, each of the 2 factors has to have at least 2 levels. And that is the simplest case, a 2 by 2 ANOVA. But when you run a 2 by 2 ANOVA, you're actually performing 3 separate tests. Those tests are a main effect of A, a main effect of B, and an interaction between A and B. Let's look at an example. Let's say that we have males and females taking some low dose or high dose of caffeine, and we're measuring their energy levels, say. Males might take a low dose of caffeine and have a mean energy of 3.05. Males might take a high dose and have a mean energy level of 5.58. Females could take a low dose of caffeine and have like a 1.71, and if they take a high dose, they could have a mean of 8.25. When we want to compare these four conditions against each other, we want to see whether there's any differences because of dose, any differences because of gender, and whether there's some kind of interaction between dose and gender. In other words, we might say, does the level of dosage cause different effects for males and females? Just eyeballing this, hopefully you can discern that that might be the case in this situation, because males taking a low dose and a high dose improve just a little bit compared to each other, but females taking a low dose and a high dose actually increase quite dramatically. And so the gender of the individual influences how the dosage impacts their energy levels. Here I'm going to show you I'm going to show you a raw data table. We've got still here the males versus the females and the low dose versus the high dose, just like I showed you on the last slide. But within each cell, I'm going to list all the individual scores that made those means. So here we've got participant number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the second group, males with a high dose of caffeine, you've got subjects 11 through 20. And then here in this group, the females taking a low dose, you've got the subjects 21 through 30. And females taking a high dose, you've got subjects 31 through 40. Each of those participants has a score, an energy score associated with him or her. If I compute the average of all the scores in this cell, the cell mean is that 3.05 that I showed you on the last slide, and the standard deviation I've listed here for every cell. So, in cell A1, B1, you can see listed here, the cell mean is 3.05. If you average all of these 10 scores, the cell mean for those males taking a high dose is 5.58. The mean down here is this, and the mean over here is this. If we want to compute a main effect, we have to compare what are called the marginal means of one of the variables. So if we looked at the difference between males and females, we would average all of these 20 scores that appear in both cells. And we would compute the mean of all 20 males, regardless of their dosage, as 4.315. And if we wanted to compute how much the average energy level of females was, we would compute all 20 of these females' scores together, ignoring their dosage, just all 20 females, and we would say the average level of energy for females is 4.98. If we wanted to compute a main effect for dosage, we would compare the low dose versus the high dose, ignoring the males and females. So we would compare all 20 of these low dosage people, regardless of their sex, and we would compute it as 2.380. That's their energy level. And if we computed all 20 of the high dosage participants, ignoring their sex, we would see that their mean energy levels were 6.915. So as you can see here, a main effect is the effect of a single treatment factor or variable. It compares the levels of that variable. So in this situation, we've compared men versus women, ignoring, or we might use this phrase, collapsing across dosage. We don't care about dosage when we're comparing this mean versus this mean for men versus women. And then later, we also compare the low dose patients versus the high dose patients, ignoring their gender. So we compare low dose versus high dose regardless of their sex. If you wanted to graph the main effective dose, here I've gone back to our original abbreviated table, you can see that the main effective dosage is to compare 2.38 versus 6.92. Those are the means of dosage regardless of their sex. And you could say 2.38 versus 6.92. That's a main effect. A main effect, remember, is when we're comparing the levels of a single factor. We could also compare the main effect of gender. In this case, it's 4.32 versus 4.98, ignoring their dosage, just comparing the sex. So all the males combined, regardless of their dosage, had an energy level of 4.32, and the females had a mean of 4.98. Remember, though, that I said when we run a factorial ANOVA, we actually make three comparisons. One's the main effect of A, a main effect of B, which we just talked about, and the third one is an interaction between A and B. An interaction means the effect of one factor depends on the level or the value of the other one. So you can't just interpret the main effect in isolation because it depends on what's going on with the other factor. If you see in a graph non-parallel lines, like for instance if they cross or they converge or diverge in a graph, then that indicates that an interaction is occurring. Now they don't actually have to cross, okay? For instance, they could just be very perpendicular but not actually cross. They just can't be parallel. So non-parallel lines, they could cross or they could just be like alligator mouth, that they're just not parallel to each other. That would mean that an interaction is occurring. Typically we call this the A by B interaction. We don't actually use the letter A and the letter B. I'm just substituting in right now letters to represent the fact that we put in some word here for factor A and a word here for factor B. So for instance, in this case, we would call this the sex by dose interaction. Sex by dose. So here we've got sex and here we've got dose, and we would call this interaction here the sex by dose interaction. The larger this angle is between the two lines, the more likely the interaction will be to be statistically significant. So you're looking to see whether it crosses or whether it's not perpendicular, and how big this angle is. And if they're very far apart and not parallel, then you're likely to find that there's a statistically significant interaction. I'd like to walk through several examples of what this looks like. In each of these examples, you will find that I'm asking whether there's a main effect of A, a main effect of B, and an interaction. So I'm going to show you the first example here. We've got a data table that is factor A and factor B. These are levels 1 and 2 of factor A, levels 1 and 2 of factor B. So if it helps you, you can imagine these as whatever variables you want. You could say this is sex and this is dose or something like that. But what I want you to answer for me is whether if factor A level 1 and factor B level 1 equaled 1, and factor A level 1 and B level 2 equaled 1, and factor A level 2 and B level 1 is 9, and factor A level 2 and B level 2 is 9, in this situation right here, if those are the means we obtain, is there a main effect of factor A? Is there a main effect of factor B? Is there an interaction? So in order to identify whether there's a main effect of A, just look here. Is 1 highly different from 9? In order to define whether there's a main effect of factor B, we look here. Is 5 very different from 5? Because remember, we're comparing these levels, B1 and B2, these levels here, ignoring A when we're doing a main effect of B. And if we're looking at a main effect of A, then we look at 1 versus 9, ignoring the levels of B, just ignoring them. So we look at 1 plus 1 divided by 2 is 1, 9 plus 9 divided by 2 is 9. If we're looking at the levels of factor B, we've got 1 plus 9 divided by 2 is 5. 1 plus 9 divided by 2 is 5. So we're taking the average of these two conditions, and we see that it's 5 versus 5. So, is there a main effect of factor A? Yes, 1 and 9 are very different from each other. Is there a main effect of factor B? No, 5 and 5 are not different from each other, so there's not a main effect of factor B. And then finally, we have to ask, is there an interaction? So I've graphed over here the lines for levels 1 and 2 of A, and separate lines here for conditions 1 and 2 of B. So just because this is our first example, I'm going to map from the table into the graph what's going on. A1, B2 is 1. A1, B2 is 1. A1, these two lines are B1 and B2. So we've also got B1 as one of these lines as well. I think this black line is B1 and this dotted line is B2 because this black line is closer to the label B1. So here we've also got A1, B1. A1, B1, it's also 1. So we plot both of those points at 1 and 1. If factor A level 2 and factor B1 is, if we're looking at the comparison there, then we would find that it's 9, and that's what that point is, and the other one is also 9, and that's what that point is, and so these two appear at 9. If you look at these lines, we have to ask, are they parallel? Yes, they're parallel, so does that mean there's an interaction or no interaction? There's no interaction. So, in answer to the question, for factor A, there's a main effect, 1 versus 9. For factor B, there's not a main effect, 5 versus 5, no difference. And factor, is there an interaction, A times B, or A by B? There's not, because these two lines are parallel. Alright, moving forward, I have a lot more of these examples, but after I show you each example, I just want you to pause the video and work through it yourself to figure out, is there a main effect of A, is there a main effect of B, and is there an interaction between the two? So here's the next example. Pause the video and ask yourself, main effect of A, main effect of B, interaction. Hopefully you saw that there was no main effect of A because these two marginal means right here are the same. There is a main effect of B because those two means right there are different. And there's not an interaction between the two factors because these lines right here are parallel. Alright, work through this example. Is there a main effect of A? Is there a main effect of B? Is there an interaction? Hopefully you saw that there is a main effect of A because 3 and 7 are different. There is a main effect of B because 7 and 3 are different. But there's not an interaction because those lines, again, are parallel. Okay, work through this example. Main effect of A, main effect of B, interaction. Hopefully you saw that there's not a main effect for either of the conditions, and there's also not an interaction, because 5 and 5 are the same, 5 and 5 are the same, and those two lines are parallel. So there's no main effects and there's no interaction in this situation. What about here? Main effect of A, main effect of B, interaction. Hopefully you figured out that there is a main effect of A. Those are different. There's not a main effect of B. Those are the same. And there is an interaction because those lines cross. They're not parallel with each other. They're perpendicular, or relatively perpendicular. What about here? Hopefully you figured out that there's a main effect of A and a main effect of B and an interaction. Because here in this situation, these lines are not parallel to each other. They don't cross either. Well, I guess they kind of, if this continued on, they would continue to cross here, but remember, the lines don't have to cross in order for there to be an interaction. They just have to be not parallel. All right, work through this one. Okay, there's no main effect of A, no main effect of B, and there is an interaction. These are the same, these are the same, and this is not parallel to each other. So there is an interaction, but there's no main effects of either condition. Work through this example. Okay, there's no main effect of A, those are the same. There's a main effect of B, because those are not the same. And there's an interaction, because those are not parallel. You should have noticed, maybe not explicitly, but as I pointed out, hopefully you recognize in retrospect that we just saw every possible combination of main effects and interactions. Sometimes there can be a main effect of one and not a main effect of the other. There could be an interaction or not, and it's independent of whether there are main effects or not. So this suggests that main effects and interactions are independent of each other. Even if we know there's a main effect of A and a main effect of B, that doesn't mean there will be an interaction. And if there's no main effect of A and no main effect of B, there still could be an interaction. Interactions supersede main effects. By which I mean, once you know that you have an interaction, it would be disingenuous and somewhat dishonest to talk about the main effect on its own, as if those differences were what mattered. Let me walk through an example to show what I mean. Let's say that we ran this study before and after therapy, and we compared males and females, and we saw that therapy works for females and it doesn't work for males. If that were the case, we could compute a main effect of A and a main effect of B, and we could compute the interaction. But if we found the main effect of therapy, it would look like this. Before versus after is the average of the pink and the blue here, so this is this level right there, and the average of the pink and the blue here after therapy, which is in the middle, or that level. So before we were averaging the pink and the blue points, and after we're averaging the pink and the blue points right in the middle, and if we carry these lines over, then after therapy their level would be here, and before therapy their average level would be here, if we're ignoring their gender. So the main effect of therapy, just alone, ignoring gender, is before and after. It looks like, wow, the therapy worked. After therapy, they were better than before. If we looked at a main effect of gender, we would find that females are better off than males. Why? Because we would average here in this situation the 2 points where the blue are and the 2 points where the pink are. So we would average this point of blue and this point of blue. And if you average those two together, it meets in the middle, and we carry this across to there. If we averaged the first point of pink and the second point of pink, that meets in the middle right about there, and we could carry that across to the pink level. So you'd say females are better off than males. But now we have to ask that question. We have to ask the question, are these interpretations even true? Well, no. People do not always get better after therapy. Only females get better after therapy. Males didn't change at all. So to say people got better after therapy is kind of disingenuous. It's kind of misleading. And to say that females are better off than males is also disingenuous, because look at before therapy. The females and the males were the same. They had the exact same mental health outcome. The same mental health levels here before the therapy started. So to say that females are better off than males is really not true. It's only true after therapy. So if you find a significant interaction, you should still report your main effects, but don't talk about them, don't interpret them, because they're no longer meaningful, even if they're statistically significant. Only the whole story, only the interaction can be interpreted once you know you have one. If we finish a factorial ANOVA, we need to write it up as if for publication in the literature, in which case we would report the mean and standard deviations for each of the conditions. Usually this would be in a table or a graph due to the complexity of the design. And we would report the results of a hypothesis test for all three terms. We would report the main effect of A, the main effect of B, and the A by B interaction. Even if this is not significant, we would still report it. Even if this is not significant, we would still report it. If this were or weren't significant, we still report it. We report all three of them independent of each other, independent of whether they're significant. So for each term, we need to include an F statistic, the degrees of freedom in parentheses, a p-value, and an eta squared. An example would be like this. The means and standard deviations for all the treatment conditions are shown in Table 1. And then we would actually have to have a table, which I didn't put on this slide, but you get the point. The two-factor analysis of variance showed no significant main effect for time control, comma, F in parentheses the degrees of freedom equals whatever the F is, then comma P greater than 0.05 because it's not significant, comma eta squared, whatever that is. This is a percentage of variability. And then we could continue the sentence with another comma. We could say, because remember where we picked off was we'll pick up where we left off, which was that the two-factor analysis of variance showed there was no significant main effect for time control or for presentation mode. And so here we have another not significant F statistic, P greater than 0.05, and then we end the sentence with a period. And then we continue, however, the interaction between factors was significant, and we would report here the F statistic, whatever that is, and its p-value less than 0.05, and the eta squared. Okay, so again, I reiterate, if you have a non-significant F and a non-significant F and a significant F, you report all three independent of whether they're significant or not. But it might be that this one's significant and these two aren't. You'd report all three anyway. If this one's not significant and this one is and this one's not, it doesn't matter what they are. You report all three when you run a factorial ANOVA. Because you've performed all three, you must report all three. All right. Here, we're wrapping up. We've just got a couple of practice problems. So, before we end, I want you to look at each of the following factorial designs and decide how many factors there are and how many levels there are of each factor. So you would write something like a 2 by 2 or a 3 by 4 by 2 or whatever it is, remembering that the number of factors is represented by how many of these numbers you have. Like here, this is a 1, 2, 3 factor ANOVA, and this is a 1, 2 factor ANOVA. And each of these numbers represents the number of levels within the variable. So what I've done is gone to the literature, found 3 examples of studies that employed a factorial ANOVA. And I'm going to report to you the abstract of those studies. In some cases, just for simplicity or clarity, I've revised the wording of the abstract a little, but these are real studies. And I want you to get practice for how in real life these factorial ANOVAs might be, like what kinds of questions they might be investigating and how they work. So, after you finish figuring out the number of levels in each factor and the number of factors there are total, draw the table to depict all the conditions. So for example, that might look something like this. Remember back to when we had like a factor, therapeutic alliance with weak and strong, and a treatment that was before and after, and a variable of sex, which was male and female. And because we had 3, we had to draw a 3-dimensional figure. And because there was a 2 by 2 by 2, we had to put 2 cells on each of the dimensions. This is the kind of thing I want you to draw to reflect what's going on up here. whatever the situation you've written out is, whether it's like a 3x4x2 or whatever. Okay, so let's work through this scenario. The first study. This study sought to determine if a woman's appearance influences perceptions of her ability to perform a job. Undergraduates rated a photograph of a woman that was either dressed professionally or sexually. The undergrads were also told that the woman was applying to be either an office assistant or a CEO. Participants rated the photo along several dimensions such as grade point average, organizational skills, leadership, dependability, and intelligence. And all of these measures were combined into one competence measure. All of those were combined into one thing, competence. And the researchers found that a sexually dressed CEO was perceived as the least competent. So, I want you to answer these questions, pause your video, and do the best you can, pushing play when you figure these answers out and you're ready to go. Hopefully you discerned that the number of independent variables, or the number of factors, was 2. The 2 factors were dress and job type. We can know that from looking up here where it says that undergraduates rated a photograph of a woman that was either dressed professionally or sexually. And then they were told what kind of job the woman was applying would either be an office assistant or a CEO. So that's the second type of independent variable, or the second factor was job type, office assistant or CEO. We asked the question also, are there any between subjects variables within subjects? Both of these are between subjects. None of the participants looked at multiple women. They were shown a photograph of a woman who was dressed either professionally or sexually, and they were told what kind of job that one woman was applying for. And then the study was over for that person. Another student was brought in, another undergraduate student was brought in and shown a picture of a different woman, and that woman was dressed either professionally or sexually and told a kind of job type. So both kinds of variables were between subjects with different participants, different subjects. This is a 2x2. Why? Because the first factor, dress, had 2 levels, professionally and sexually. So that would be the first one, 2. And then the second one would be the job type, office assistant or CEO. 2 levels of job type, so that one would be here, 2. And because both of these were between subjects variables, we have to say this is a between subjects ANOVA. If we had some within subjects and some between subjects, then we would call it a mixed ANOVA. But if it's only one type and both factors are the same type, then we just call it a between subjects. Or if they were both repeated measures, then we call it a within subjects. But whatever, if they're one type, then we just stick to either of these terms. But because both of them were between subjects independent variables or factors, then we call it a between subjects ANOVA in this situation. The cell for this would be a 2x2, so if you drew it out, it would look like a cell of 4 different conditions. It would be crossed in the middle like that, and it would have, the job type professionally versus sexually, and the dress type is professionally or sexually, and the job type is office and CEO, so there'd be 4 different cells. Now, I'm not sure how many of you got tripped up by this principle up here where we were taking together the grade point average and the organizational skills and leadership and all that stuff and making it a competence measure, but the average of all of those things is actually our dependent variable. This is what we're interested in the effect of. So we're looking to see whether people's competence depends on, or dependent variable depends on, the independent variables of dress type and job type. All right, let's try this next one. This study sought to determine whether a third party could discern romantic interest between 2 strangers. And by third party, we mean somebody who's not on a date with them, just watching a video of them. So they're watching a video of two strangers. To test this, male and female observers watched video clips of speed dating situations to determine the individual speed dater's level of romantic interest toward the speed dating partner. I'm going to stop there and kind of explain that sentence. Some people who watched the videos were males, and some people who watched the videos were females. They watched a video of two people at a speed date, and they were trying to figure out how interested the folks were in each other. Like, how interested was the woman in the man, and how interested was the man in the woman. Participants observed clips of different lengths. Some of them were 10 seconds, some of them were 30 seconds. And from different parts of the speed date. Some of them were in the beginning, some of them were in the middle of the date, some of them were at the end of the date. Each participant rated 1 long and 3 short video clips. And they might have been, again, somewhere, like the long one could have been in the beginning or the middle or the end, and the short ones could have been the beginning, middle, or the end. But the point is that they watched some of long and some of short, and they watched some that were at different stages. The researchers also coded for the participants' gender, male or female. So whether, remember, some of the people watching the video were males and females, and that mattered to the researchers. And their relationship status, whether the people watching the study were single or in a relationship. Results indicated that participants were able to discern romantic interest at above chance levels. So you'd expect that just by chance people would not be able to discern somebody's romantic interest very well unless there was some cues being given off, some visual cues being given off, which would allow us to kind of tell how interested somebody was, and so that would mean that we were better than chance at discerning their romantic interest. The length of the clip did not influence accuracy, although the part of the speed date, whether it was the beginning, middle, or end, did. So pause the video, answer these 4 questions, and then resume when you're ready. Alright, I want you to recognize that I see this is a very difficult problem. And if you struggle with it, I don't want you to feel bad, because this is very complicated a description here. But the answer to the first one is that there are 4 independent variables, 4 factors. They are the length of the video, the part of the video, the participant's sex, and the participant's relationship status. So, the length of the video, the part of the video, the participant's sex, and their participant's relationship status. Are there any between subjects variables or within subjects variables? Hopefully you recognized that the length of the video and the part of the video were repeated measures. They were within subjects because participants watched both some long and some short, and they watched some videos that were in the beginning, some that were in the middle, some that were in the end. So those are within subjects variables. There were also between subjects variables. The participant's sex, male and female, you don't come into the study and be both of them. You're either one or the other. And your relationship status, you don't come into the study and be both. The researcher's not going to force you to change your relationship status mid-study so that he can make you in both conditions. Rather, some of the people came in and were single, and some of other people came in and were in a relationship. And so those 2 factors are between subjects variables. So we had 2 that were within and 2 that were between. Therefore, we have to conclude that this is a 2 by 3 by 2 by 2. 2 by 3 by 2 by 2. Why? Because the length is 2 conditions, the part is 3 conditions, the sex is 2 conditions, and the relationship is 2 conditions. So 2 by 3 by 2 by 2. And then we might answer the question, is this a between subjects, a within subjects, or a mixed ANOVA? This is a mixed ANOVA because we have some that are between and some that are within. And because we have both types of factors, we're calling it mixed. It's both. If you were to draw this out, you should have drawn two cubes that were like 2 by 2 by, like 2 by 3 by 2, and then labeled them with the different conditions of the study. So it should have been like two cubes that were each three-dimensional. One would have, like one side would have two conditions, one would have two conditions, and then another side would have three conditions. Alright, this is the last one. To evaluate whether imagined ostracism can be a painful experience for individuals, researchers recruited one real participant and then put him or her in a room with two confederates. That means fake participants. They're actually researchers, but they seem like they're actually participants. And the participants, the real ones, were told to interact with the, quote, other participants, who really were actually researchers pretending to be participants, via texting, until they were directed to stop. So please go in the room and text with the other people until we ask you until we tell you that the study's over. The Confederates, the fake participants, asked a few questions, like, do you exercise? Remembering this is over text message, so they would ask things of the other participants, and then they would ask the participants if they smoke. For half, the Confederates created what's called an in-group effect by telling the participants, oh, we do too, or we don't also. Whatever the participant said they did or didn't do, then the Confederates answered they did the same. It didn't matter what the Confederates really did, they were just pretending. So they were just telling the participant, yeah, we smoke too, or no, we don't smoke either. For the other half, they created an out-group effect by telling the participants that they did the opposite. So they would be like, oh, we don't. Or, like, if you do, then they would say, oh, we don't. And if you don't, then they would say, oh, well, we do. Then the Confederates either kept responding to the participant, or they stopped responding to the participant's text messages after the initial conversation. So they would ask something first, like, do you exercise? And then they would ask about smoking. And then they would either create this in-group effect or this out-group effect. And then they would either continue or stop responding. After the study, the blind coders analyzed the content of the text messages to see what kinds of statements were made by the participant, and found that participants made more provoking types of comments when they had been ostracized, that is, made to feel like they were part of the out-group, and not only part of the out-group, but also they stopped communicating with the participant. So, for example, they might say something like, are you people not speaking to me? I am being oppressed. And, how come no one is messaging me? A post-manipulation survey showed that those participants who were ostracized also reported a worse mood, a lower sense of belonging and control, and lower self-esteem. Whether the participants perceived themselves to be part of an in-group or out-group did not influence the ostracism effect. So it actually didn't matter whether they were told to, whether the Confederates said, yeah, we smoke too, or, we don't smoke. If they ignored the participant after that, they felt ostracized and didn't know why. And it didn't matter whether they were told that they were part of the out-group or whether they were part of the in-group. They just felt bad for nobody else texting to them. Okay, so go ahead and pause the video, answer these 4 questions, and continue when you're ready. So the answer to the first question here, how many independent variables or factors are there, is 2. There are 2 factors. The first one is, I don't know what to call it. Let's just call it similarity. It's whether we are the same as you or different than you. We smoke like you or we don't smoke like you. So we'll call it similarity. And there's in-group and out-group. You could also call it group type, in-group, out-group, whatever you want to call it. The second factor, the second independent variable, is I don't know what to call this one either. Maybe inclusion? Well, it's not necessarily inclusion. It could be exclusion. So maybe this isn't a word, but let's call it clusion. It could be inclusion or exclusion. They kept responding or they stopped responding. So they either kept responding to the text message or they stopped responding to the participants' text messages. And so we've got this other variable of clusion. Are there between subjects variables, within subjects variables? Hopefully you noticed that there were only 2 between subjects variables. Participants came in this and they were either told, oh yeah, you're like us, or oh, you're not like us. And they were either kept responding to or stopped responding to. And so each participant who came in only experienced one of these and one of these. Nobody was exposed to repeated measures, to multiple conditions. So we would say this is a 2 by 2, because the first factor had 2 conditions, in group and out group. The second one had 2 conditions, kept responding or stopped responding. So the first one has 2 levels, the second one has 2 levels, so we'd say it's a 2 by 2. And then finally, is this a between subjects, a within subjects, or a mixed? This is a between subjects because both of the conditions were, this factor and this factor, both of the factors were between subjects, and so we just call it a between subjects ANOVA. All right. When you go through your homework, you'll notice again that, like I said at the beginning, there are no computations for this homework assignment. Everything is conceptual, the same kind of way that I walked you through conceptual exercises and a conceptual understanding of this factorial ANOVA here throughout the module lecture. You'll see that your homework asks of you the same kinds of things. So I wish you luck, and please, as always, reach out if you need help.